Hi everybody, welcome back. Today we're going to take a look at lesson 10.3, enthalpy. Okay, so our aim is 10.3, what is enthalpy? I'm going to go over the question of the day and then the homework from last time. And then our lesson is about potential energy diagrams. And we've got optional homework 25 and then a video demo called Elephant's Toothpaste. So in this unit, we're studying kinetics and equilibrium. So we started off by thinking about how we can picture reactions as these little particles bouncing around like ping pongs, and how if we picture, especially gases that way, we can kind of picture what might affect the rate of a chemical reaction, what could speed it up, what could slow it down. And in our last lesson, we talked about what can lead to effective collisions. And we learned 6 factors that affect the speed of reaction by affecting the number of effective collisions. In this lesson, this is kind of part 1 of 2, looking at how can you tell if a forward or backward reaction is more likely to occur, or you can kind of think of it as what might make a reaction just sort of happen spontaneously on its own. So question of the day here is, which of these chemical reactions do you think is endothermic? Which is exothermic? How can you tell? This is a harkening back to the very first unit of the year, the physical nature of matter, when you did your hot pack, cold pack in the lab. And you might recall that endothermic means energy in. So that would be a cold pack. It has to suck energy in. And exothermic means the energy is exiting. So we would feel heat because the energy is going into us because it's exiting the reaction. So that would be like the burning match as an exothermic reaction. All right, so here's the answers to homework 24 along with some of my notes about how I solved the problems. And you can either pause the video on each slide or you can look at the PowerPoint. Great. Okay, so today's aim is 10.3. What is enthalpy? Or how can we predict if a reaction will go forwards or backwards? Part 1 of 2. Okay, so let's take a step way back and think about, remember, what does energy have to do with bonds? All right, so remember your model of the magnets. Does it take energy to pull them apart or put them together? It takes energy to pull them apart, right? You have to put energy in to break a bond. The atoms want to be together. They are more stable in a bond, right? So when they come together, they release energy. When you break a bond, you have to put in energy. So breaking a bond, remember, is endothermic, whereas making a bond, letting 2 atoms come together, is exothermic. And this is one of the things that is most often confused in chemistry by students and teachers and people who've been chemists a long time. It's just easy to forget, and in a lot of ways it's not intuitive. So remember that breaking a bond, you have to pull the atoms apart from each other. That takes energy. That's endothermic. Making a bond is exothermic. As you know, in a chemical reaction, we have both. We have breaking of bonds, so there's an endothermic component, and we have making of new bonds, so there's an exothermic component of every reaction. Now, whether or not a chemical reaction will occur often has to do with, well, is it easy to break those bonds? Do you get a lot of energy out when the new bonds are made? It has to do with whether the overall reaction is endo or exothermic many times. So think about reactions that just happen on their own, like this reaction. This is metal rusting. You know, you don't have to try hard to get metal to rust, right? If you just leave it out in the rain, it'll start resting on its own. So thinking about that, whether or not a reaction just kind of happens on its own, is going to have a lot to do with what's called the enthalpy of the reaction, or in other words, what's stronger, the bonds of the reactants or the products, or in other words, is it endo or exothermic? So let's remind ourselves these terms. Endothermic reaction means overall it absorbs energy. Endo, energy in. So if you touched an endothermic reaction, to you it would feel cold because it's sucking your energy into it. So if it's overall sucking energy in, that means overall it's taking more energy to break bonds than to make bonds, because breaking bonds takes energy. So what's stronger, the bonds broken or the bonds formed? We'll get back to that. Recall that an exothermic reaction is one that releases energy overall. Energy is exiting, right? And to us, it feels hot because if we're near an exothermic reaction, the energy is leaving the reaction and going into us. So we say, ooh, hot, exothermic. Okay, so back to the endothermic reaction. What's going to be stronger, the bonds broken or the bonds formed? Well, overall, it's absorbing energy. That must mean it takes a lot of energy to break those bonds. That means the bonds broken are stronger. In our exothermic reaction, it'll be opposite. It must mean you're making things with really strong bonds, and so that releases a bunch of energy. Yeah. In the case of combustion, you're always making carbon dioxide and water. In carbon dioxide, 2 sets of double bonds. Those are really strong. That's going to release a bunch of energy. All right, so enthalpy is the term we use for describing if a reaction is endo or exothermic, and by how much. It's how we quantify it. It's abbreviated with delta H. It's the overall amount of heat energy absorbed or released in a reaction. So it's helpful a lot of times to visualize it in a graph. And we call these potential energy diagrams that show us the heat of reaction, or the enthalpy of reaction. Those are synonymous. Okay, so in a potential energy diagram, we start off over here with the potential energy of the reactants. Then we know we have to break bonds, put energy in. That part of the reaction we call the activation energy. That's the energy needed to make the reaction go. Or in other words, getting the molecules in the right orientation and breaking the bonds so that then they can come together in a new way and react and make new bonds. Then the energy over here is the energy of the products after they've made new bonds. So in this case, you'll notice that the reactants started off with this amount of energy. They ended up with less energy. So they ended up overall giving off energy to the universe. Even though they had to gain a little bit of energy here to get going, they ended up giving out more than they gained. And that difference between the energy of the reactants and the energy of the products is the enthalpy of the reaction, or the heat of reaction. So you could just calculate it by subtraction. Take the afterwards amount of energy, subtract the before amount of energy, and that tells you the heat of reaction, or the enthalpy of the reaction. You can kind of think of these diagrams as looking at a sledding hill, right? You have to first carry your sled to the top of the hill. That's where you put the energy in, right? The activation energy. Then once you get to the top, now you're full of potential energy. You can slide down the hill. And then at the bottom, there's your energy of the products. Not all hills are created equal, right? Okay, so let's take a look at what the enthalpy diagram, or the potential energy diagram, would look like for an endothermic reaction versus an exothermic one. For an endothermic reaction, energy in, delta H is positive, meaning you end up with more energy in the products than you started with in the reactants. So in this case, this shows a endothermic reaction. Let's find the exact quantity, the heat of reaction. So that'll be potential energy of the products, which is right here. Looks like it's about 350, minus potential energy of the reactants, which looks like it's about 200. So we can see it gives us a positive number overall. We gained 150 kilojoules, endothermic reaction. This is where you climb a huge hill, you put so much energy in, and then you just get a little ride out. Not that fun for sledding. That's an endothermic reaction. You still do get a bit of energy because made new bonds, energy was released. But more energy was put in to break bonds than energy was released when you made bonds. So endothermic overall. Here we've got an exothermic graph of an exothermic reaction. So here you notice the reactants, the energy of the reactants is higher than the energy of the products. How much higher? Let's find the heat of reaction. So again, we'll start with the energy of the products, which in this case looks like it's about 10 kilojoules. And then we'll subtract the energy of the potential energy of the reactants, which looks like it's about 40 kilojoules. And now we get a negative number, negative 30 kilojoules. That shows us it's exothermic, or in other words, it's giving off energy to the universe. So to go sledding, you hiked up the little hill, that's where you break the bonds, activation energy. Whee! Then you got to sled all the way down, way more fun, released way more energy overall than it took to climb up the hill. That's an exothermic reaction. All right, which do you think would just be more likely to spontaneously happen on its own? Exothermic reactions, right? It would be easier to accidentally sled down a big hill than to accidentally climb a hill, right? Or it takes less energy for a exothermic reaction to happen because as it releases energy, it provides its own activation energy. So it can kind of keep itself going. Whereas an endothermic reaction can't. It has to keep getting the energy to keep going. So this is going to be the first piece of the puzzle of what is it that makes a reaction go, or what makes a reaction happen. So exothermic reactions are more likely to occur than endothermic ones. Okay, what does adding a catalyst do to the heat of reaction? A catalyst was one of the 6 factors we learned about last time. We know that adding a catalyst speeds up the activation, speeds up the rate of the reaction. And we said it was because it decreases the activation energy, but I didn't explain what that was. But now you know, activation energy is this hump, right? It's where you break the bonds and get ready for the reaction and then make new bonds. So the activation energy with a catalyst is going to be a lot lower because the catalyst helps the particles already be facing the right way. So they don't have to put in as much energy to break the old bonds because they're already perfectly oriented. So in this case, we've got the activation without a catalyst is that pink line. The activation energy with a catalyst is that blue line, much lower. You can see this reaction is probably going to be way faster because it's more likely for the particles to have enough energy for this reaction to happen with the catalyst. So adding a catalyst, as you know, lowers the activation energy. This speeds up the reaction, but you'll notice what it didn't change. It didn't change the energy of the products or the energy of the reactants. So overall, this minus this, the heat of reaction or the enthalpy of the reaction remains unchanged. So do you think you could take a reaction that's usually endothermic and make it become exothermic by adding a catalyst? No, you cannot. Catalyst only changes the activation energy. It doesn't change the overall enthalpy of the reaction. Okay, so one of the last reference tables we'll look at this year is reference table I, heats of reaction. It's on page 5. it shows you the enthalpy of reaction or the heat of reaction for a bunch of different reactions. I'll show it to you in the next slide here. So here's a bunch of different reactions, and then it shows you the enthalpy in kilojoules. So let's see if we can find the most exothermic reaction of them all. This will be the one with the greatest negative change in enthalpy. Yeah, I think it's this one. Do you recognize which type of reaction this is? Yeah, this is a combustion reaction. Hydrocarbon plus oxygen makes carbon dioxide and water. Makes sense that it's really exothermic, right? We know combustions give off a lot of heat and light. Cool. You can notice this other combustion is also pretty exothermic. Let's see if we can find the most endothermic reaction of them all. Biggest positive number. I think it's this one. Oh, wait. Oh, here's even bigger. So this is carbon plus hydrogen makes C2H2. I can imagine it would be really hard to break all those strong covalent bonds in solid carbon. Picture a diamond. Hard to break that up. So I can see why that would be endothermic. It would be hard to break those bonds. You'd need a lot of energy to make that happen. All right, let's do an example here. We've got a potential energy diagram. Part A, which is which? Potential energy of the reactants, potential energy of the products, and activation energy. Well, number 1 there is potential energy of the reactants. Number 2, that's the activation energy. And number 3 is the potential energy of the products. Part B, if the potential energy of the reactants is 56.12 kilojoules and the potential energy of the products is 7.29 kilojoules, what is the heat of reaction? To find the enthalpy of the reaction, we subtract products minus reactants. So that'll be 7.29 minus 56.12. We get a negative number, negative 48.8 kilojoules. And looking at this overall, we can tell, okay, that makes sense that it's negative because it ends up with less energy than it started off. All right, so then is this reaction exo or endothermic? Well, negative change in energy means it's losing energy or releasing energy to the universe. That means exothermic. Okay, and using your answer from part B, which reaction might this be from table I of your reference table? So our answer to part B was negative 48.8 kilojoules. Let's take a look and see if that matches anything from table I. If you look way down at the bottom here, negative 48.83. That's the reaction of lithium bromide turning solid, dissolving and turning into lithium and bromide aqueous. Awesome. Okay, so for our summary demo, I would of course love to do this one in class for you, but since we're learning from home, I was pleased to find out from Mr. McGee actually that Miss America this year, for her talent portion, did this demo and won. So we've got a video of her performing this reaction. She did it when she won Miss Virginia and then Miss America. And we're going to picture, what do you think the potential energy diagram would look like for this reaction, the elephant's toothpaste demo, with and without the potassium iodide added? So let's take a look here at Miss America's demonstration.
Hydrogen peroxide is a chemical that's breaking down slowly all the time. Have you ever wondered why it's packaged in a brown bottle? It's because the light from the sun speeds up its breakdown, so it's packaged in a dark bottle to protect it from light. But light and time aren't the only things that break down hydrogen peroxide. Catalysts are chemicals that are used to speed up reactions, and what we're about to watch is the catalytic decomposition of hydrogen peroxide.
if you couldn't hear her, she said that in these bottles she's got hydrogen peroxide. She's about to add a catalyst to each one. She's also got dish soap and food coloring in here. And she was saying that hydrogen peroxide breaks down on its own, which you guys know that's what we used in the Tiny Rockets lab to make oxygen gas, but that you can speed it up with the catalyst. Okay, here we go.
So be careful. Don't try this one at home. Now, in my flask are concentrated hydrogen peroxide, food coloring, and dish soap. I'm about to pour in potassium iodide, my catalyst, which will start the breakdown. Now, this reaction is really simple. It only produces three things: water, oxygen gas, and heat. The heat is formed from the breaking of the bonds within the hydrogen peroxide molecule, and the oxygen gas is trapped in the dish soap, which forms the foam, so we can see how far the reaction has progressed. Now, the next time that you see a bottle of hydrogen peroxide, I hope you impress your friends with what you've learned.
Yay, Miss America. Awesome. So that's the elephant's toothpaste demo. You can see she added a catalyst and it way sped up the reaction. So if we were trying to sketch this, do you guys think it would be endo or exothermic? She said it releases a bunch of heat. That is true. This is definitely exothermic. So if I were to make it exothermic, I'd want the energy of the reactants to be higher than the energy of the products. Okay, so let's say that's the normal version. Now if we had the catalyst in there, the potassium iodide she added, that's going to decrease the activation energy. So then the curve would have the same energy of the reactants, but a lower activation energy, same energy of the products. Awesome, thanks guys. That's it for today. There's optional homework number 25 on the next few slides. You can pause the screen to work on those, and or you can find them in the PowerPoint. Thanks, have a great rest of your day.